Well, thank you very much. It's really an honor to be here and to get a chance to talk about the work that we've been doing on sustainability. So this talk is joint work with several of my students and postdocs, particularly Rebecca Hutchinson and Dan Sheldon, our postdocs, and Wenqing Wang is another faculty member, and Claire Montgomery is an economist who's working with us. So if we look at the Earth's ecosystems, they're very complex, right? The biosphere, the ecosphere is a very large and complex system, and I think we have to admit we haven't managed it very well. We haven't managed it in a sustainable way. And I think there are several reasons for that. One is that we really lack knowledge of the function and structure of the system. There's a very interesting paper by Doak et al. In 2008 about entitled Ecological Surprise, or something along those lines, in which they go through about 20 case studies of cases where either something very surprising happened, like there was a sudden increase in the population of some fish, and then 2 years later a sudden decrease, and no particular understanding of why that happened, or cases where we've attempted to intervene in an ecosystem to try to improve it, and instead had some completely surprising outcome result from that. I mean, one example that we have right now in Oregon is the northern spotted owl, and I assume it lives as far north as here as well. There's been a huge amount change in how we manage our forests in Oregon to try to preserve habitat for this owl. But in the meantime, another owl has moved into its territory called the barred owl, which is much more aggressive. And so, despite all the things we're doing to try to manage the spotted owl, the barred owl may take over anyway and drive it extinct. And that was not at all considered when people were originally building that policy. So one reason that we're having trouble managing our ecosystems is that we just don't know how they work, and it's hard to manage them. Another reason, of course, is that we've often focused on just a part of the system. So we might have said, well, we'll set aside this piece of forest, but we didn't. But we ignored, say, the human and social components, and so people ended up poaching out of that forest or damaging in various ways, and we didn't really look at the larger problem, the social, the economic, or even the spatial aspects often. And I think the third reason that we fail to manage our ecosystems well is that, particularly in agriculture, what we've done is to drastically simplify the system. For instance, in crop agriculture, we typically try to remove all species except the one of interest, and then we rely on exogenous inputs of fertilizers and pesticides and herbicides to maintain and control that simplified system. And that turns out to be very expensive in energy and also phosphorus and things like this, which are actually now becoming quite an issue. So we'd like to move to more sustainable practices in all these things, and I think the message I'm trying to communicate right now is that computer science can help. We have a lot of technologies and techniques that can make a difference. So, for example, on the first problem of building better models of the function and structure of ecosystems, we have sensors of all different novel types of sensors. We have machine learning techniques so that we can build complex models of those systems. The problem of focusing on just a subsystem, again, we now have tools to be able to study much larger systems, and that may include things not only building models of them, but things like mechanism design and optimization to try to help those larger social biological systems function better. And then in something like agriculture, it's a similar message. We have tools to be able to monitor and manage much more complex systems than have been allowed in the past. And that may permit us to use more cheaper biological ways of doing pest control, of providing fertilizer, and so on, and allow us to have more sustainable agriculture. But it's not that we have these tools all ready to go. There's a lot of computer science research that needs to happen. As was mentioned in my introduction, I'm part of a joint project with Cornell University that we call the Institute for Computational Sustainability. It's funded by the National Science Foundation in the U.S. And we have adopted this name to indicate the study of computational methods that can contribute to sustainable management of the Earth's ecosystems. And we're interpreting that broadly to include not only the biological and physical aspects of ecosystems, but also the social and economic components. And by and large, I tend to formulate it, and this is probably showing my machine learning biases, in terms of this pipeline. Let's see, I do this, right? That starts with data collection and moves through model fitting and eventually to creating policies and executing those policies. And so that's the way I'm going to organize this talk, is to talk about this pipeline. I'll start by giving you examples of work, mostly by other people, illustrating the various components in this pipeline, and then I'll talk about 3 areas where we've been doing work ourselves. So the first thing that I want to talk about is sensor placement. This is something we have not been working on, but the world is a big place, and we can't afford to measure all of it. In fact, a big problem with a lot of ecological work is that it divides up by different organisms. So bird watchers go out and they find where the birds are, but they don't look at what the insects are doing, where it turns out birds eat insects. The insect people measure the insects, but they don't see what the plants are doing. A lot of insect larvae eat plants. And so one of the big challenges actually to measure entire ecosystems, measure all of the moving parts, the nitrogen and phosphorus, the carbon and so on, and all the organisms. And of course that's complicated. In addition, we have to decide, well, where should we be observing? And there's been some very nice work, mostly coming out of Carnegie Mellon, Carlos Gestrin and his student Andreas Krause, who's now in Switzerland, where they've looked at this problem of sensor placement. Where should we put sensors in order to best achieve certain objectives? So we might want to, for instance, in this case, it was a question of detecting a pollutant in a plumbing system, a sewer system, or water supply system. Another one might be to try to improve the accuracy of a model. We might want to be trying to improve our causal understanding of the system, and so on and so forth. And one of the key tools they've been using is this notion of a submodular function, which is a function over sets that has a diminishing returns property as the set gets larger and larger. So in this case, the set of sensors that you put out, the information you collect decreases with each additional sensor. And so they're able to then solve what might appear to be a very complex combinatorial problem efficiently using these kind of techniques. Because it turns out for large classes of submodular functions, the greedy algorithm gives you very good results. The second point in my pipeline is data interpretation. So often in a lot of applications, the raw data we get from the sensors really isn't usable, particularly, for example, if it's image data or acoustic data, raw GPS tracks from cell phone location information. That needs to be processed, and a lot of sort of classic computer science work happens here. It's really not unique to this area. One example from my lab is I have a visitor right now, Qing Yao from China, and she's puts out light traps in rice fields and captures the insects living in this field, mostly moths in this case. And then they photograph them. These have been put down on a glass table, and they're photographed from both above, where this image was captured, and below. This is the other camera, out of focus, below the table. And now she wants to be able to analyze each of these bugs and then count up, how many of each species is in the image, because it's that count of species that's the most interesting thing she'd really like to get. The pixels are not so useful. And I've had a project in my lab for the last 7 years that we call the Bug ID Project, where we're trying to do these kinds of things. A third step in the process is often data integration. So one of the other things about ecosystems is that we have a large variety of ways of sensing them at very different scales and with very different properties. So, for example, when we're trying to build models that, say, describe the distribution of species or understand the spread of disease, invasive species, and so on, we often need to collect data from many different sources. So we might need land cover data that might come from Landsat, and it's collected every month, and it has a 30-meter resolution, or data from the MODIS, which is another satellite that maps the whole Earth every day, but at a much coarser resolution, and on and on. Data from the census, data from digital elevation models, so each of these different sensing mechanisms has certain modes of failure, certain biases, certain scales, and this all needs to be integrated together. Now for map data it seems simple because you have like a universal coordinate system of latitude and longitude, but for a lot of other data it's not nearly so clear what kind of coordinate system you want to put it into. the fourth point in the pipeline is model fitting, and of course I'm a machine learning person, so this is my core area. In ecology there are several different kinds of models that we'd like to fit to data. The simplest kind are these things called species distribution models. And there we want to basically create a map of the distribution of a species around the planet or around the country. And without, these are static models, it's just a snapshot of where we think the species is. The other two kinds of models are dynamic models that try to capture something about the movement and behavior of the species. One kind are focused on places, and those are called metapopulation models. And the idea here is that you might have a set of sites or patches or islands or mountaintops that are good habitat for a species. But the species may be able to disperse from one site to another. So the species could go locally extinct in one place, but then get recolonized from its neighbors. And obviously if you drill down to a small enough scale, like a 1 meter square, that becomes an interesting model for almost any species. So this is one thing that you'd like to focus on. And then the third kind of model really, instead of looking at the place and seeing who's there, focuses on the organism and sees where it is. Okay, and so those are migration or dispersal models. And here we'd like to model the trajectories of organisms over time, the timing of their movements and so on. And of course, a whole range of machine learning tools can be used here. I wanted to show you one example of a fitted model that's been done at the Cornell Lab of Ornithology, and it's for this bird that's called the indigo bunting. And let's see, is it animating here? Yes, it is. Okay. Of course, this is for the U.S., and this is a sort of movie going over time through the year. So the indigo bunting spends its winter times down in the Caribbean and Central America, and then here we are coming along, and around March or April we'll start to see it coming northward along the Mississippi Valley, and then it spreads out through the eastern United States and up into Canada. When we have this problem with our models, when we can't figure out where the birds have gone, we just say, oh, they must be in Canada somewhere. Or where they came from, oh, they must be... Anyway, so the next time it goes through, let's look at places like Atlanta and so on, St. Louis, as cities, and you'll see that this bird actually avoids the cities. So there's little black places where those cities are that are not preferred habitat for this species. So this is a fitted model. You're actually seeing a series of snapshots. It's not really a dynamical model. It's just using time as one of the prediction variables. And this data is fitted to data reported by bird watchers to something called eBird. So if you're a birder, you can join eBird and upload data for us. They got 3 million points uploaded in May this year, which was their new high. And so they're getting usually about 1 million reported sightings a month. And so this is a tremendous data resource that we're trying to use. Then the next step in this development is, so suppose you have a model of the distribution of species. For instance, this is some work done in New Zealand by John Leithwick and colleagues. And so this is, the black part here is New Zealand, these things here. And then these are areas where fishing is taking place for a species called moro moro. And the red dots are where the fish was caught, and the gray dots was where they tried to catch it and failed. So this is what the data looks like. And those big blue lines are the exclusive economic zone of New Zealand. And so then here's the fitted species distribution model that John came up with, where he's estimating the mass of the catch, it's the biomass of the catch in the fishery. So this is another example of a nice species distribution model. Where are these fish? Where do you find these fish? But then the next question is, well, from a policy point of view, if we want to create biological reserves where we will have no fishing, where should we put them? And so that's an instance of trying to optimize a policy. And so here he sort of prioritized places using, there's a sort of standard tool out there for trying to optimize the placement of reserves. And I'll remember what its name is in a moment. Anyway, this is if he disregards costs of the fishing industry and just tries to maximize the effectiveness of the reserves. Here is if he takes full consideration of the costs to the fishing industry of different kinds of reserves. And you can see that they're quite similar. So you can achieve your conservation goals and still be able to achieve your fishing goals in this case. And then finally, there's the question of policy execution. You've designed this beautiful policy, now you want to execute it. And so, as a computer scientist, your first thought is, well, it's easy. We just repeatedly observe the current state of the system, and then we choose, according to our policy, what action we should perform, and we execute it. And then we repeat. But of course, that's rather naive, because one of the most challenging things about ecology is that our models aren't very good. So the model that we built our policy on probably could use improving, and over time, as we gain more experience with the system, we'll need to be updating our policy. So we really need to take an approach of sort of continuous improvement of our models, and then continuous improvement of our policies. And I think a huge challenge here, I mean, again, those of you who know about partially observable Markov decision processes would say, well, we can just formulate this as a POMDD and solve it. Well, you can formulate it. Solving it is going to be more of a challenge. But I'm interested and intrigued by the possibility that we might be able to develop policies that are robust to our lack of knowledge. In computer science, we have a bunch of tools, basically probabilistic modeling, Bayesian type methods, where we try to represent our uncertainty, right, as probability distributions over, say, spaces of models. And those, in the immortal words of Donald Rumsfeld, our former Secretary of Defense, are the known unknowns. But I'm also wondering whether there are things we can do about the unknown unknowns, about the things that we have not modeled, and that we don't know to even model, like the idea of the barred owl showing up that we didn't anticipate in our model. So it was a zero probability event, but it happened anyway. And I think there are some ideas from non-Bayesian statistics, more in the classical statistical realm, that tries to robustify things in that way. But I think there's a lot of scope for doing robust optimizations of various kinds as well. Of course, one thing to do is model more of our unknowns, more broadly adopt the basic techniques we already have. Okay, so that's sort of the review of what's in the pipeline, going from placing sensors all the way to executing policies. And now I'm going to drill down and just look at three areas where we've been doing work in my lab. One is in the data interpretation phase on something that at first glance seems kind of mundane, which is automated data cleaning. And then we'll talk a bit about a model fitting challenge that arises particularly when you're doing field observations of animals like birds. And this is where you need to explicitly model the observation process itself, because your observations are biased. And finally, we'll talk about the problem of managing fire, which is a policy optimization problem. The first work is done by my graduate student, Ethan Dzerzhinsky, and so we pause for a little acknowledgement and also an advertisement. He's graduating later this year, and he'll be on the job market. But he's done he's a great guy, and has done really interesting work on the following. So Oregon State University operates an experimental forest called the H.J. Andrews Experimental Forest. And we do a lot of ecological work there. It's one of the long-term ecological research sites, so we have temperature and precipitation records back 100 years and so on. And that data is now collected by these meteorological towers, and they have a lot of instruments on them, but in particular they have these 4 thermometers that are allegedly at 1.5, 2.5, 3.5, and 4.5 meters above the ground, but that doesn't look like it. So anyway, that's what they tell me. And so we have this temperature data. And of course we also have precipitation and solar radiation and snow depth and many other things. But sensors, of course, even these sensors, which are permanently in place and are designed to be very robust, unlike a lot of the sort of smart dust sensors that you expect will break, these sensors develop problems. And so here are some examples. This is from one of our towers. And this is the sort of daily pulse, right? In the daytime it warms up and at night it cools off. And it's kind of fun because the thermometer that's closest to the ground, which is the black line here, is the coolest at night and the hottest in the daytime. So the thermometers kind of flip their temperature readings. This particular thermometer, though, has a broken sun shield. And so the thermometer is still reporting temperature, but it's no longer air temperature, it's the temperature of the surface of the thermometer when the sun is shining directly on it. So it's heating up and being very hot in the day. Those peaks are too high. At night, it's very accurate. So that's one kind of fault that we see. Here's another thing that happens, and this was at the upper lookout tower that I just showed you. And here, I'd like you to guess. So here we have one thermometer seems to be flatlined, and another one is maybe the red one, the second one up is kind of damped. Any idea what might be going on here? Yes? Yes! It is no longer an air temperature sensor, it is a snow temperature sensor. So the real problem is the metadata is wrong on this thermometer, right? It's still functioning correctly, but its semantics has changed. So then, right here, what happens is that it starts to rain. So here it was reading, something like -1, -2, I don't know. Well, you have a better view on it. Here it's at the triple point because it's saturated water-ice mix. And then it starts to return to normal because there's a huge melting event here, and we have the biggest flood we've had in the time I've lived in Oregon. So this was an important event. But it's an illustration of how I think it's very hard to anticipate all the things that could go wrong. I don't have a picture for it, but the most subtle error that happened with these thermometers was during maintenance, they interchanged two of the cables. So this is, again, a metadata error. The 2-meter thermometer is really 3, and the 3 is really 2. And so if you look at any one signal in isolation, of course, it's perfect, because it is perfect. So, and another instance that's a bit like this one is a water stream temperature sensor that in summertime the water level drops and it becomes an air temperature sensor. So we wanted to take an approach to this problem that would not you could treat this kind of problem as a diagnosis problem, right? You have a set of known faults, you model each one, and then you ask what fault is most likely to explain the observations here. And that works fine for all the sort of known things that could happen, but we wanted to, again, try to handle things that we hadn't anticipated. So we wanted to, oops, I have pictures, animations, I forgot that. So what do we want in an ideal data cleaning system? Well, we'd like a system that can find all of the anomalies in the data and mark them. So this is some other sensor data from a site in Switzerland, and these little red hash marks on the bottom are places where the model has correctly concluded that there's, well, they're not all correct, but most of them are correct, correctly concluded there's something wrong. These are much cheaper sensors, and they're a lot messier. You look at this spikiness and flatlining and so on. We also have some just data transmission dropouts where the signal disappears. So you'd like it to find all of those. And then in addition, you'd like it to do what's called imputation, right? Which is to, when it thinks a sensor is bad, can it infer what the sensor would have seen? For instance, by looking at nearby sensors, which we can often do in these sort of sensor networks. And so these red curves here are now all these imputed values. So those are the two things we'd like it to do. And so the basic approach we take is kind of the standard approach one would take in a probabilistic modeling setting, which is to build a latent variable model or a hidden variable model. So we have our, so this is a kind of basic network, and I don't know how many of you are familiar with them, I assume some, but each of these things is a different random variable or a different value that we're measuring. So this is the observed temperature, and this is and it's colored gray, which means we actually do observe it. We know its value. The true temperature is a hidden variable, and then we also have a hidden variable that's the state of the sensor. Say the sensor can be either working or broken. And so if ST is equal to 1, it means the sensor is working fine. If it's 0, then it means it's broken. And so then we might adopt a probabilistic model that says if the sensor is working and the true temperature is T, then the observed temperature will have a normal distribution whose mean is T and whose variance is some small variance. So in other words, the sensor is measuring the temperature with a small amount of noise. But if it's broken, then it has a mean of 0 and some humongous variance. So we're just saying that it's no longer connected to the true temperature, it's just some very random value. So that's a simple model, and with this kind of probabilistic model, assuming you had some prior beliefs about what the true temperature was, and maybe some prior beliefs about the state of the sensor, you could then use probabilistic inference to do the to solve the two problems that I mentioned. One is you could do anomaly detection and ask the system the query, what is the most likely state of the sensor given the observation? So this is, what's the most likely value of argmax of ST, the argmax of the probability of ST given the observation OT. You could also do imputation by saying, what's the most likely value of the true temperature, this hidden variable here, given the observation. So that's our dream. Of course, this model is pretty impoverished because we don't really have any way to connect it to other sensors or to even to the same sensor in the past. So let's improve the model a bit. Let's first make it a Markov model. So the temperature at this time period is going to be similar to the temperature 15 minutes ago, with maybe some small Gaussian random walk away from that. So that's going to be one Markov chain. And also the sensors don't break every 15 minutes. They tend to be broken, well, they tend to work for a long time and then be broken for a long time, and then work again for a long time. So we can model that also somewhat as a Markov model. So now our query turns into this. Find me the most likely state of this sensor from time 0 all the way up to the present, given all the observations from time 0 up to the present. That's a bit more complex query, but in fact, well, we'll come to that moment. The other thing we can do is copy this network and say we have two thermometers now, thermometer number 2 and thermometer number 1. And now we can couple their true temperatures. So we can say the temperature at thermometer 2 is going to be very related in some way, correlated to the temperature at location 1. In particular, if they're like the 1 meter and the 2 meter thermometers on the tower, it turns out they'll be, the thermometer 2 will be slightly higher in temperature at night and slightly lower during the day. So now we can have a model, and ideally we'd like to be able to put tens or hundreds of thermometers into this kind of a model. So there's only, of course, there are some computational challenges. This is often the case in probabilistic modeling. We can write down models, but we can't always solve them. In this case, it turns out probabilistic inference is infeasible for the single sensor model because we end up with an inference that grows exponentially in the length of that time series. So the solution we've adopted there is basically sometimes called filtering, where we are going to pose a query to the model. Say at time 1, we'll say, what's the most likely value of the sensor at time 1? And then whatever value that is, we're going to say, that's right, that was the state of that sensor, so we commit to it. And then at time 2, we say, okay, now what's the most likely value of the sensor, given the observation, and that should say S1, and what it was at time 1. And we'll say, and even if the probability of that is only 0.51 versus 0.49, we'll still commit to it and say, okay, that's the state of the sensor now. So it's an approximation. It does not get the right answer in all cases. But of course, these queries are very easy to ask, and so it's not, it works very well in practice. Although we do have to also bound, if a sensor is broken for a long time, our model allows it's no longer constrained by the observations. So it's just, its variance grows and grows and grows, and we have to limit that. Because eventually it will be able to explain even the noisy wrong values. With the multiple sensor model, the inference is still infeasible because it's exponential in the number of sensors. And so the solution for this is actually still open. We're experimenting, for those in the know, with using a greedy algorithm coupled with expectation propagation. And so far that looks like it's going to work for us. So here are some results. This is for a version of the model where we actually allowed 4 different sensor states, very good, good, bad, and very bad, that had progressively larger and larger variances and weaker connections to the true temperature. And we can see that our model correctly figures out that there's something wrong with this thermometer in the daytime. It marks these red things are the bad, and even a couple of very bads at the very peak temperatures. But it's also correctly identified that at nighttime, this thermometer is usable. So if you were doing a study that only needed nighttime temperatures, you could still use this sensor. What the humans do that are doing the data cleaning manually, which is the current practice, is they would just mark this entire period as broken, which is conservative, and so we can get a more fine-grained sense of what's going on here. For the multiple sensor version of the model, we want to actually learn the structure of the correlations among the sensors. So we use a more or less standard Bayesian network structure learning algorithm to learn this Bayesian network over these 6 thermometers that were deployed in Switzerland along a stream here. This is a DAG. It doesn't look like it here, but it is a standard Bayesian network. We're using conditional linear Gaussian distributions for those reasons. And so here's the results, which you've already seen before, of how the model did on a related problem in Switzerland. And it's doing reasonably well. There are a few problems that it runs into. So our model doesn't really look at this flatline sensor reading and say, something's seriously wrong with that sensor. In fact, whenever it's predicted, here's its predicted temperature for that sensor. And you can see whenever the predicted temperature gets close to the flat line, it says, oh, it's not broken. So it thinks it's not broken right in here, and it's not broken right in here. So, you know, this is the weakness of our model right now. We need a model, I guess, that says that normally we expect some variability in a sensor, and when it's flatlining, it can't possibly be measuring anything. But it doesn't. We don't capture that right now. So now we're working also on the challenge of introducing a lot more sensor values, sensor readings that are not temperatures, and this raises a lot of challenges. And the other thing is really we need more of a multi-scale analysis. Not all sensor faults show up at a 15-minute time scale. Some of them you really need to be looking over much longer periods. And so there's still a lot of work that needs to be done here. Okay, so that's the work on the automated data cleaning. I should say that, you know, these towers are a relatively small number of towers that are out there and have been out there for a long time. But we're in the midst of a sort of sensor revolution, right, in all fields, but certainly in ecology. So we'd like to put out, you know, thousands of sensors out there. And whereas it was feasible for a human being to look through all of the sensor data when there were only, say, 3 towers, that's completely impossible when we put out thousands of sensors, especially if they're cheap ones that break easily. So we're really going to have to move to this automated sensor technique. Okay, well, the next thing I want to talk about is model fitting. And this is work of a postdoc of mine, Rebecca Hutchinson, who's also, so this is another advertisement. She's finishing up her postdoc, 3-year postdoc with me in just a few months, and she'll be on the market as well. And we've been looking at this problem of building species distribution models. Now, when you build species distribution models from something like fish capture data, it's quite good because fishermen are quite good at catching fish. But if we're doing something like trying to detect birds, they actually like to hide from you. And so you have this problem of imperfect detection. So here's a little cartoon of the imperfect detection problem. Suppose that this is some sort of landscape, and it's divided into cells or squares, and some of those squares are occupied by this species, and some of them are not occupied. And we want to understand what are the factors. Let's say, you know, maybe it's the distance to a stream, or maybe it's a distance away from a road, or something like this, the proper kind of vegetation, whatever, that determines what is the suitable habitat for this species and what is not. So if we go out bird watching or we go out surveying for this species, we can't survey everywhere. So we will, if we only survey inside the black squares, we won't see some of the birds because we didn't look in those squares. And we can kind of compensate for that because we know where we looked. But the second problem is, even when we go looking, some of the birds are hidden. And the idea here is not that plants suddenly appeared, but that the birds went and hid inside the vegetation. And so what can we do about this? Well, one thing we can do is make multiple visits. And it could be that on a second visit, the bird that was hiding here is now, we detect him, but maybe we miss one of the birds we saw before. But if we can pool data across multiple visits to a site, maybe we can uncover the distribution better. And so the kind of data we get looks like this, multiple visit data. So let's suppose that we have 4 different sites that we go to visit, A, B, C, and D, and each of them is described, say, by what kind of vegetation is there and its elevation and various properties like this. And it turns out those 3 forested sites all, in reality, are occupied by this species, and the grassland site is not. But the first time we go out observing, it's a rainy day and we go out at noon, which is a very bad, those are very bad conditions to detect birds. They're usually more detectable at 5 in the morning than they are at noon. And so it turns out, not surprisingly, we don't detect anybody that day. We go out another day, and it's a clear day, and we're out at 6 in the morning, and we detect the bird in site A and B, but we didn't catch the one in C. We didn't see it. And we didn't see the one in D either. So far we have a 0-0 detection history here and here, and we can't tell the difference between those two. And let's say on the third day, it's a clear day, but we're a little late. We didn't get out quite so early, and so we miss the first, we see the first one, but we miss these other two. So from this multiple visit data, we'd like to estimate our detection probability. What's the probability we'll detect the bird if it's there? And so based on the cases, we know that the bird is occupying these two places because we saw it at least once in these two cases. So we might think our detection probability, 3 out of the 6 opportunities, we saw the bird. So our naive estimate of our detection probability is 50%, right? It's 3 out of our 6 times we saw it. Because we don't know about this guy here. Whereas in reality, our detection probability was more like 1/3, right? Because 3 out of the 9 possible cases, we saw the bird. So using our naive estimate isn't very good, but we can use a probabilistic model to understand this. And so this is a hidden variable model that was developed by Darryl Mackenzie and colleagues a few years ago. So this is not original with us at all. And the idea is that we have a hidden variable z sub I. So I is indexing the number of sites, and this outer dotted box is like a for loop over sites. It says for each of these different sites, the site has some attributes like elevation and vegetation, and that determines its occupancy probability, O sub I. And then Zi is 0 or 1 if the site is occupied or not occupied or occupied. This part of our model is our observation model. So WIT, we make big T visits to each site, and each time we go, we have some attributes of our visit. Time of day, the weather, maybe. And that determines our detection probability on that visit. And YIT is our actual observation. Did we see the bird now? And so we like to fit this model to data. And let me name this function over here as our occupancy probability function f. And that's the model we actually care about. Where is the species? And then we have a detection model here, which we'll call G, which is our detection probability. We need to fit both of these. And we can do that if we parameterize these, say, in the work that Mackenzie did, they often used a logistic regression type of parameterization. But let me step back for a moment and talk about a kind of emerging challenge problem in machine learning, which is how can we merge the strengths of probabilistic graphical models like this with the strengths of flexible modeling in machine learning. So probabilistic graphical models have many, many advantages, and we've really seen a huge revolution in the field over the last 30 years. They provide us a really nice language for describing models, and we can do learning and reasoning in them just by doing probabilistic inference. And they also let us talk about hidden variables, like latent variables, as you've seen in both of the models I've showed you so far. But they do have some disadvantages. The designer of the model needs to choose the parametric form of the model for each of the different probability distributions. And often that means deciding on the number and the form of the interactions, and also typically involves then pre-processing and scaling your data so that it matches those assumptions. And in general, they're not very user-friendly. On the other hand, in sort of a parallel strand of machine learning, which does not do probabilistic modeling, there's been a lot of development of very flexible models. So one technology is classification and regression trees, like the C4.5 and CART algorithms. And these are great sort of off-the-shelf, out-of-the-box algorithms. You can apply them to just about any kind of data. You don't have to pre-process your data. They discover what interactions exist, and they can achieve high accuracy if you use boosting or some other ensemble techniques. And another, of course, family of methods are the support vector machine family. And these require some data pre-processing and transformation, but they have very powerful ways of tuning the complexity of the model to the complexity of the problem. So we really like to merge these two and have both the strength of probabilistic modeling which lets us talk about hidden variables and so on, and the strength of these very flexible models that are also very user-friendly. And so there's been a lot of work in the past, I guess, 5 years or so in the machine learning community trying to achieve this vision. There's been some very cool stuff in the sort of kernel support vector machine world where they're trying to figure out how to embed probability distributions in these mathematical objects called reproducing kernel Hilbert spaces, which sounds very high-tech. And they succeeded. The best paper at the machine learning conference 2 years ago was showing how to do this for hidden Markov models. And there's been some other work on what are called non-parametric Bayesian techniques that are based on, say, Dietterich process methods. The approach we've been pursuing in my lab is we love trees, classification regression trees. So we're doing the work. We had a paper at AAAI this year on how to fit this occupancy detection model using regression tree techniques. And so we're going to model these two functions, f and g, as boosted regression trees, building on work by Jerry Friedman in 2000, where he showed how a sort of generic algorithm for constructing a boosting algorithm given any differentiable loss function. And so we were able to do this by basically coupled functional gradient descent techniques. And so let me just show you some of the results from that work. We wanted to compare our approach, which we're calling BRT, boosted regression trees, with the logistic regression parameterization that was done by Darryl McKenzie. And we evaluated these on 12 bird species, and we also made up 3 synthetic species so that we would know what the right answer was. One of the big challenges methodologically in working with hidden variable models is the variable is hidden, so how do you know whether you're getting it right or not? So you generally have to rely on simulation studies. And we're using data from New York State, so all of our observations for when people visited and what they properties of each site are real values from these actual observations. So here's just to give you a flavor, one of our synthetic species, where we said the occupancy probability is going to be proportional to a linear function. This is called a log linear model, an exponentiated linear function, but it's nonlinear in the individual predictor variables. And the detection probability is intended to capture higher detections in the morning and the evening and some other nonlinearities. So this is a species that should be challenging for the logistic regression model, which assumes linearity inside the exponential to fit. So here are results for this synthetic species, and we're comparing 4 methods. So on the left-hand side here, we have purely supervised, so-called supervised learning approaches, where we don't have a latent variable. So we just try to go directly from the inputs, that would be x and w, to the output y. And so what we're plotting is on the horizontal axis in each of these is the true probability of occupancy at the site, and the vertical axis is the predicted occupancy or detection probability. So in this case, for the supervised models, they don't actually predict z, they predict y, and so they're basically under-predicting z because they have to explain all of those false zeros. They treat them as true zeros, and so they get fooled by that. But over here, these are the boosted regression tree models. And as expected, the occupancy, the latent variable model with boosted regression trees is working well. Because what we'd like to see is all of the points lined up on this diagonal line. So please ignore that point right there. And we get a nice diagonal behavior. Up here we can see there's a lot of scatter, and that's because this is a linear model and it can't handle those nonlinearities. So this is one piece of evidence that suggests that by modeling the component probability distributions inside this latent variable model using boosted regression trees, we can have our cake and eat it too. We can have both the flexible modeling of the tree methods and the probabilistic modeling that we get with graphical models. So we have an R package that's kind of an alpha test right now, but we'll be distributing soon. So the last thing I want to talk about in the shortest time is our work on policy optimization for managing fire in Eastern Oregon. In the eastern part of Oregon is a high desert area, or it's much drier than the west, of course. And people believe that the forest should look something like this. So these are large ponderosa pine trees. And the thing to notice is that the floor of the forest is basically clear. It's easy to go walking through this forest because you just have some low shrubs and so on. And this landscape is maintained this way by having frequent low-intensity fires. They're what are called ground fires. So they just burn out the vegetation on the forest floor, but they don't climb up the trees and burn the tops of the trees. Those would be called crown fires, where they burn the trees. And so these trees are adapted to fire. They have nice fire-resistant bark. And so this results in this kind of a landscape. But in the U.S., since around the 1920s, or even slightly before that, we've had essentially 100% fire suppression. Right? Politically, the U.S. Forest Service was created with the mission of preventing forest fire, rather than the mission of having a healthy natural ecosystem. And so the result has been, it turns out you can postpone fire, but you really can't prevent it. And so after, whatever it is, 80, 90 years of fire suppression, we have forests where they don't look like this at all. Unfortunately, I don't have a picture, but they have lots of trees of various different heights. So shrubs and grass, and then for instance, lodgepole pine trees that have invaded into the area where these large ponderosa pine are. And these provide what are known as ladder fuels, so that if a ground fire breaks out, it can then climb up these trees, reach the crown, and then create a devastating fire. Because of course in the summertime, the whole forest dries out. And so it is prone to fire. And so the question is, and the result now is that we have these huge catastrophic fires that leave the landscape where they completely denuded and even can cause oxidation of soil organic carbon, which means that it takes a very long time for the forest to recover. So we'd like to manage these fires and somehow help the landscape return to its more natural state. And so we've been working with the Forest Service in a study area that's part of the Deschutes National Forest, which is in eastern Oregon. And they divide up the forest, this is our study region, into little patches. So each of these little patches is a sort of homogeneous, and they're called management units. And we'd like to manage the landscape. Well, what does it mean to manage the landscape? Well, each year we could take certain actions in these patches. We could do nothing. We could actually harvest the trees and sell them, which would make some money. But unfortunately, when you harvest the trees, you actually increase fire risk. For the next 20 years, you have young, sort of fragile trees growing, and then when they dry out, they actually are even more prone to burning. Or you can do what's called mechanical fuels treatment, where you go in and essentially hire people to remove all those understory trees. And they're not so useful for timber, but they might be useful for energy production and other kinds of wood products. But it turns out that's a net money loser. It costs a lot to do the fuel reduction treatment. So we can't afford to treat everything. So we have this decision problem. What management units should we treat? And we can kind of do this as a game against nature. Each time step t, we have our turn to move, and so we can observe the current state of the landscape. You know, what's the age of the trees, and what's maybe the accumulation of fuels. And then we can choose some areas to treat. So we might choose this pattern of treatment in the landscape here. This is actually from a model, not ours, but a group that published at least in a Canadian journal, led by Way. And then nature has its turn, and it gets to ignite fires stochastically, and then those fires burn stochastically and change the landscape. And then it's going to be our turn again in the next time step. So we can formulate this as a large Markov decision problem in which we have some state space and some action space. And this is where the problem comes in. Because let's suppose that in each of these management units, we just say the trees can fall into one of 5 states, depending on how old they are. And we'll assume they're all the same age. So this is a huge oversimplification. And similarly, that the amount of fuel we could discretize into 5 levels. So then each management unit can be in one of 25 states. But there are 4,000 units, so that's 25 to the 4,000th power states that the whole landscape can be. And similarly, our action space is large, because if we have these actions, do nothing, do a fuel treatment, harvest the trees, or maybe harvest plus doing the fuel treatment, we have 4 to the 4,000th power actions, action vectors to choose among at each time step. So this is a huge problem that we don't know how to solve. There's been some work, as I mentioned, this paper by Wei et al. From a couple of years ago. They looked at a single time step version of it. So they just said, suppose we can treat once, and then we'll look at what happens with all future fires. And they were able to formulate this as a mixed integer program and solve it using Cplex. But it's only for one time step, whereas we really want to think about a dynamic plan, right, where if we didn't treat a place this year, we have a chance to do it again next year or the year after that. And so fortunately, I've hired this postdoc guy, Mark Crowley, from here, and he's going to solve this problem. And so you can invite him back in a couple of years to find out how he does it. Okay, so let me just summarize then. I've talked about this pipeline from sensor placement all the way to policy execution, and then tried to talk a bit about data interpretation problems. There are many others here. We are doing some work where we're trying to analyze the weather radar in the U.S. In the U.S., the Doppler weather radar picks up clouds of birds, and we think we can use that to do things like modeling bird migration, especially if we combine it with the sightings of bird watchers. And there are also several other kind of image-related projects there. And then I talked about model fitting and some of the problems we've been doing with explicit observation models. There are many other model fitting problems. Another huge one that we have to deal with is that it turns out bird watchers are people. And that means they live in cities. And they tend to go bird watching close to home. So we have lots and lots of observations around New York City and Los Angeles, very few in North Dakota, and so on. And so we have, this is known as spatial sampling bias, and it's a severe problem, and we want to figure out how we can still try to fit a model that's accurate despite that. And then I've talked about the policy optimization problem. We're also looking at problems of managing disease and invasive species, which also can be viewed as these large spatial Markov decision processes. So the main message, of course, I think is that there are many opportunities for computer science to make a difference in sustainability and encouraging improving our ability to manage the Earth's ecosystems. But many of these are also challenging research problems, so there's very exciting research to be done. Of course, there's also a lot of things where we can just take our current techniques and apply them. Just a couple of other notes. Some of you may have heard of this thing called the Computing Community Consortium or something like this, which is a part of the something called the Computing Research Association. And in the US, they are sponsoring computational sustainability tracks, not just in the US, but in the International Conference of Machine Learning, AAAI, and I think in some other conferences as well in the coming year. We had one last year at AAAI that was a huge success. And so they're going to offer like travel grants and things like this to encourage that. And then our Institute for Computational Sustainability can be found here at computationalsustainability.org. And we also are having workshops, for instance, at NIPS this year, and possibly a conference in Europe next summer. So thank you very much for your attention, and thank you particularly to Ethan and Rebecca. And the FIRE team is Claire Montgomery, her former student Rachel Hauptman, and my PhD student Sean McGregor. And of course, this is all funded by the US NSF. So, thank you. I'll answer questions.
Can you comment a little bit on how you test your model fit on real data sets?
Well, so with the with the bird problems. Well, we look at how well we fit the data, of course, and we, say holdout likelihood. So we see how well we can handle data that wasn't used to fit the model. And there are issues with dealing with the spatial sampling bias too. So we lay down a network of grid cells, and then we try to sample the same number of points from each cell. Some of the cells are empty though, so we can't do that for all of them. So those are the two things we're doing. But I think we have to rely on simulation studies where we try to generate realistic data that has the same kind of statistical properties, and then see how well we can recover the right model for those situations. One other thing we can try to do is also cross-compare our results with we're relying mostly on these citizen scientist volunteers in the eBird project that are going out and collecting data. But there's also something called the Breeding Bird Survey, which is done every year in May and June. And the people that do that are much higher, very skilled birders. And so we can cross-compare how well we're able to do with them. We can also look at some sanity checks. So we had a paper last year at ICDM, the data mining conference, where we also built a model of the expertise of each individual birder, based on things like how much do they report, and do they report birds that are identified only by their songs as opposed to by eye, and things like this. And then we look and see how well that works. And because at least in New York State, the Lab of Ornithology people, they know a lot of these birders, and so they can give us like supervised answers on that. And we were able to recover their judgments about who are good birders. And so we can then compare their data with the novice data and see how well they work. One of the open questions is, with a lot of these citizen science projects, you have a small core, like it's the classic 80-20 thing, where 20% of your birders are fantastic, and you can rely on them. Should you just throw away the rest of the data? That wouldn't be very nice. And besides, those 80% other novices are covering a lot more space. But it's still an open question whether we can combine their low-quality data with the high-quality data and get an overall better result than we could just by figuring out who the good ones are and throwing away the novices. But as with all real science, you have to look at lots of different pieces of evidence to try to figure out whether your models make any sense. Yes?
I have a very, very low level of detail question, a very high level of detail question. So the low level one is, there was a data point there and you said, forget about that one. I'm just curious, why would one want to forget about this particular data
because
point?
it was just off the diagonal. No, I don't really know what's going wrong with that. A big problem with the latent variable model is that the two model components try to push problems off onto the other component.
Right.
So for instance, the occupancy model can just try to say, this species is everywhere, and the reason there's some zeros, well, that's all failures of observation.
Right.
The observation model can say, I see everything, and the reason there's zeros is because the species wasn't there.
Right.
And sometimes we notice in our simulation studies that we will get something like that. Or we'll get an occupancy model that just says, probability 20% of occupancy everywhere, uniformly, it doesn't really care. So we get the kind of flat response. And so another challenge that we have is, how can you encourage a latent variable model to do the right thing? And so we're experimenting with a sort of mutual information regularization idea, where we say that each model component should maximize its mutual information with the observation, and with the hope that so they really should try to explain the observation rather than making excuses for the observation, which is kind of what they're doing now. But we don't know whether that will work or not. But it is very tricky, and I really like this work by Ben Taskar, you may know about, this posterior regularization framework, where you can put other constraints on the posterior distribution, and so that's very similar to what we're doing.
Good. Just quickly, the high-level question would be, you as sort of a leading part of this institute that has been reaching out, I think, very well to all sorts of areas within computer science. You make the point that there's huge opportunities all across the discipline, right?
Mm-hmm.
Nevertheless, having worked on this for a while, you must feel that some disciplines currently are likely to contribute more, and perhaps in a more fundamental way in the near future than others. And so I'm just wondering, what's your personal feeling about the areas that...
It seems like there's so many optimization problems. I think if we had better, robust methods for optimization, that we could make a lot of impact. Because very often, like with these, in the forest case and the fire case, there are existing simulators out there. It's quite a challenge to pull them all together. But that they really could be used to do some interesting policy work. But the people in the field are just not sophisticated about optimization, so it's beyond their capabilities to do that. And so I think that's the first thing. Machine learning, I should be saying, oh, it's all machine learning problems, but the first thing I think we need is more people in optimization. Secondly, there are lots of machine learning problems, but But there we often have an issue that our data time series don't extend back very far. And we have many generations of sensing. So, you know, the Doppler weather radar in the US is now in its 4th generation, just going to its 5th. And unfortunately, they don't deploy them with an overlap so that you could cross-calibrate them. So we have this problem of, it's another data integration problem. In Canada, we have also the problem that they filtered the birds out of the radar. So they did not archive the raw data, at least not to my knowledge. In the US, someone had the foresight to actually archive all the raw data. So, yeah, so that's a little frustrating.
Thank you.
Another high-level question. Who do you see as the clients for this kind of research? Are you working mostly with governments and policymakers, or do you see an opportunity to make this information more accessible to more stakeholders?
Well, so with the fire work, we've been working mostly with the U.S. Forest Service, and we've mostly been focusing on public lands with a single owner for all the kind of issues that's a simpler case. But ultimately, we need to consider the problem that there are multiple landholders and they have conflicts, right? I mean, if you and I are neighbors and I remove the fuels on my land, hey, that reduces your fire risk. So maybe you don't have to spend the money to clean up your field. Or if I cut my trees and increase the fire risk, you're sort of in trouble now. So we were talking this morning, actually, Kevin and I, about thinking about this from a game theoretic point of view and trying to, it's kind of spatial game. And that would then involve multiple stakeholders. Another, with our bird migration project that was just getting underway, we also want to work with the people that own and manage skyscrapers, right? Because migrating birds collide with skyscrapers at night when the skyscrapers are lit up. And so I know in Chicago, I'm not sure about other cities, they're trying to now manage the lighting in these skyscrapers to reduce that. And there's also the siting of wind farms is another issue with migrating birds. And actually the U.S. Air Force is very interested too, because unlike in commercial airlines, they do all of their training at night. And that's when birds are migrating. So they're bird-plane interactions or something. So I don't know, there are lots of different clients, I guess, that we imagine out there.
So you mentioned like what computer scientists can do, and I wanted to kind of get more of an opinion on that. Do you foresee that computer science departments will start hiring groups that are dedicated solely to computational sustainability, or do you think that this is something that will it be like machine learning?
Will it be like bioinformatics?
Or bioinformatics?
Yeah.
And
well, I hope it'll be like bioinformatics. I mean, one thing that maybe gravitates against that is that it's much more diverse, much more heterogeneous. Bioinformatics had the virtue that, at least initially, the primary data source was gene sequence data and protein sequence data, and so it was kind of like a core set of methods. But now they've branched out in all this sort of integrated systems biology that's pulling in all kinds of things, and so maybe it'll be more like that.
And then in terms of interacting with other departments, because one would claim that statistics and earth and ocean sciences have been looking at these problems now for decades.
Yes, yeah, they have.
What synergies are there and opportunities?
But they seem to, all the people that I talk to are extremely eager to have computer scientists help them. Because they know that we have much better command of the tools and the methodology and so on than they do. I mean, they have interesting modeling opportunities, and there are certain rare individuals who really can do it all. So, for instance, these latent variable models that were developed by McKenzie et al. There's a USGS, the U.S. Geological Survey Office in Maryland that really does extremely sophisticated Bayesian statistics of these kinds. But they're such an exception. Most of the, I went to my first ecology meeting this year, and it was like every talk you could see, oh, we could do that better, we could do that better. So I think we have an opportunity really to raise the quantitative sophistication of these fields and really have a big impact.
About prior knowledge, because you require prior knowledge, and there's all these experts out there who have or think they have prior knowledge, and if you don't use them, then they get upset and you really want to use them. And so how do you interact with experts and prior knowledge?
Well, what do we do? I don't know. I mean, in the case of the fire project, we're using their prior knowledge because it's embodied in the simulators that they built. In the case of the bird work, we have these 3 experts that between the 3 of them cover all the birds of North America. And mostly we've used them to help us think about what are the relevant attributes of sites and I guess what species to start with first that would make the most sense. And then they help us assess whether our fitted models are any good. So we're currently doing a sort of study. We have this hypothesis that these ideas from Dirichlet topic modeling, like latent Dirichlet allocation and so on, might be a good way of discovering ecological communities in biological data. And so we've applied it to a huge plant survey that was done in Australia, and then we're having the ecologists there judge whether it succeeded or not, because we really have to rely on their expertise to decide that. So
you're using it for their evaluating and not
right. Well,
prior
yeah, of
knowledge.
course. Yeah. The other thing that I see as a big challenge problem I didn't mention here is often in a lot of these problems there is a kind of often a mechanistic causal model out there. Now it's usually oversimple, and but if you think about what's happening, say with climate modeling, right? It's mostly based on physics and chemistry, and it would be very nice to also get some data in there. So you'd really like to combine mechanistic causal models with data-driven machine learning models. And we don't really know how to do that. I mean, there is this emerging field of sort of data assimilation where they're developing some techniques for trying to do this. But I think, for instance, modeling buildings is my favorite example. So we're in a LEED Gold building, and I understand several of the buildings here are maybe even better than that, platinum. And we have lots of sensors in the building. But I don't know about your building, but our building is using a lot more energy than it was designed for. And they have these models they use to design the heating and ventilation and lighting and so on. And we have all these sensors. Could we use their physics-based model as a starting point and then add onto it an empirical, data-driven component, and then use that to control the building and maybe get a much better result? Rather than trying to learn all the building dynamics just from the data, which requires us to sort of rediscover a lot of physics. We should be able to use that knowledge. But I don't know, in other times in machine learning, if you have enough data, sometimes you're better off just using just the data. Or using a simulator to generate fake data and combine that with real data and then fit the model to that. So we'll see. But I think that's a big challenge in a lot of these problems. We should be able to benefit from that. Same with the power grid and a lot of the smart grid things. There are models out there, but they're not very good, but they exist and we could benefit from them.
Thinking to the New Zealand fishing example, and yet the 2 different images of if conservation was sort of the priority, and taking into consideration the fisherman's concern. I was also just going to say there's sort of like a public policy perspective where, say, perhaps trying to have more conservation in one area would be easier, less expensive,
right?
Politically, if you will.
Yeah.
And so, are you planning on modeling, or are you already modeling for the expense, if you will, of actually designating this area that's not fish here?
Yeah, and this comes in really to how do you formulate the objective in an optimization problem. I have another version of that diagram that has stakeholders and objective formulation and feedback. I think a big issue there also is when we optimize the policy and we get like this pattern of patches in the landscape, we say these are the ones you should treat, and they're going to say, yeah, why? They need to have some ability to drill down and get explanations out of the optimization, and explaining an optimal solution is also difficult. And of course, there may be multiple criteria that they can't easily combine into a single criterion, right? And so then we're looking at Pareto curves and trade-off curves and trying to say, well, here are all of these things that are sort of equally good for the things you told us about, and now stare at them and think about, well, what else might you want to bring to bear in deciding what to do? So this is with the fire thing, we find that we need to then maybe apply machine learning to try to find a simple explanation for the pattern for the solution that's been found that we could explain to someone. Typically, tends to have, it has to be like a relational model of some kind that says, well, we do this because it's next to this and so on. We don't really know how to do that either. But I see the need for explanation and the need for systems that let people explore and the trade-off space and try out ideas, propose alternatives and see how they would be scored, and so on. So there are a lot of challenges there.
So when you talked about integrating data models and causal models, I was thinking about your sensor models in the first examples. You didn't use failure modes of the sensor. I mean, you just said it's either really bad or not too bad. But we do know how sensors fail in many cases. You could have various failure modes and then have an unknown failure mode.
Right, yeah.
You might get a better model because you know if it's flatlining, it's never going to come back, and the sun cover could have been broken. That's
yes.
You know, so you could have used some expertise there.
That's right. Yes, absolutely. And in fact, you'd sort of like the system to discover a new failure mode and say, oh, this is a pattern, kind of a signature. Let me add a new, add a new value to the failure variable. Particularly with a user in the loop, they could say, oh yeah, I forgot to tell you, that's what a broken sun shield looks like. I'll hang around here.
All right. So it seems like in many problems of sustainability, it's really important to have the domain expert in the loop in order to really make progress. And well, you had several examples of that. And that seems to stand in the way of scaling up to have multiple departments, many optimization people, and so on work on these problems. So what's your take on how easy it would be to have abstract problem formulations, have data, have black box functions that people can try their optimizers on, try their machine learning techniques on, and so on.
You're right. Well, of course, I think the creation of these sort of open repositories of problems has been fantastic for the field. I mean, we complain a lot about the Irvine machine learning collection, but it really did push the field forward hugely. And so I think we want to do the same thing here. So, for instance, all of the bird data from the eBird project is released in something called the eBird reference data set every year, and it's machine learning ready. It's got all the predictor variables and the responses, and so that's certainly something that we're encouraging people to try. But the optimization problems, a lot tougher, because these simulators are bulky. Like now, the simulators we're using for our forest thing are in the public domain, and so we should be able to make those available and let people work with them. But now this is computationally demanding. I mean, it's big C++ programs and so on. But that's the reality. So I'm hoping that, as our field is moving more and more to sort of cloud-based computing, that we could, create these virtual machines at Amazon you could check out, and they have the simulator and everything in them, and then you could just run against it. And maybe that's a way that we can get to a more open science model for these things. But we're not quite there yet.
So my question is a little bit more. In your model fitting approach, I guess you're assuming that your system is unchanged. You're assuming that the bird is there, but you can't see it. But if the system is actually changed because the bird is not there, how your model handles that?
Yeah, and so that, which is exactly the migration modeling problem, is maybe the bird was there yesterday, but right. In the work I showed, we made this assumption they call it the population closure assumption. There's no immigration or emigration from the sites. You have to start building a dynamical model, so that now the presence or absence is actually changing over time. And then you have to try to learn that model. And that's what we're doing with the bird migration. But really you need to start bringing in more data sources if you can. And so we're trying to bring in the weather radar where we can see birds flying at night. We can't tell what species they are, unfortunately. And also acoustic monitoring. It turns out migrating birds, many species make little flight calls, little chirps. They can be picked up by ground-based microphones, and then we can identify the species. There we can get the species, but we don't know what direction they're going. But we're hoping to combine all those different data sources to try to fit the models. But It's the migration model has the, enforces now sort of Kirchhoff's laws of birds, that a bird, you can't, invent them, bring them out of nowhere, and they have to, the flow into a node has to equal the flow out, and that brings in some additional constraint. But unfortunately, we still have the Canada problem, which is that we don't have enough observations in Canada, and so whenever the model wants more birds, it just says, oh, they must have come from Canada. When it needs to get rid of some, it says, oh, they went to northern Ontario.
That's a good place to stop. Okay, thank you.